Welcome to Delta Wave History, your sanctuary for functional historical boredom. Our focus will remain on the historical, methodical, numerical, and the procedural. This allows your mind to unwind and drift into historical details. Please adjust your volume for a consistent, even tone. We aim for a predictable vocal rhythm, devoid of sudden shifts in pitch or intensity, designed to facilitate a state of tranquil observation and sleep, if you wish. Welcome to Delta Wave History. Tonight, we are going to slowly explore the quiet, unyielding geometry of the 19th century spiral staircase. Cast iron, an alloy heavily laden with carbon, completely transformed Victorian architecture. It offered the seemingly impossible ability to be endlessly decorative while functioning as a primary structural support. Yet, as an industrial material, cast iron is inherently brittle. It possesses immense compressive strength, meaning it can bear massive downward weight, but it suffers from terrible tensile weakness, meaning it snaps rather than bends. To build a towering, self-supporting spiral staircase from such a rigid material, foundries had to rely on a hidden mathematical secret. The true stability lay not in the intense fire of the forge, but in the calculated precision of the logarithmic spiral. Let us take a moment to trace the long, deliberate path from a vat of molten metal to an elegant, twisting staircase. Imagine a late autumn afternoon in an 1860s foundry, where the ambient temperature is meticulously regulated. The central column of the staircase serves as the vital anchor for the entire structure. It is cast as a dense, hollow cylinder, precisely calculated by engineers to distribute the downward force of countless future footsteps. This central column relies entirely on simple, unbreakable compression. It stands vertically, silently accepting the burden of the treads and transferring the heavy load directly down into the stone foundation below. Now, we turn our deliberate attention to the individual treads themselves. Each step is designed as a modular wedge, essentially a fractional slice of a perfect geometric circle. The inner edge of every single tread features a perfectly smooth, circular iron collar. This collar slides meticulously over the central column, creating a snug, interlocking fit that requires absolutely no bolts, rivets, or welding to remain secure. The foundational mathematics dictate that the collar's internal diameter must exceed the column's external diameter by exactly 1/16 of an inch. This minute, calculated tolerance safely allows for the natural thermal expansion of the iron during the changing seasons. As we let our focus move outward from the column along the flat surface of the tread, the geometric complexity deepens. The outer edge of each individual step sweeps in a very specific, calculated curve. This graceful sweep is derived from the strict principles of the Archimedean spiral, effectively translated into a three-dimensional helical structure. The rise and run of the staircase must remain perfectly, monotonously consistent to trick the human eye and secure the human foot. A standard Victorian spiral staircase typically featured a vertical rise of 7¾ inches per step. The run, measured precisely at the center of the intended walking path, was often exactly 9 inches. To achieve this flawless consistency, the wooden patterns used to mold the initial sand casting had to be carved with absolute, unflinching precision. A master pattern maker would spend long, quiet weeks shaving mere millimeters of mahogany wood in a dust-filled workshop. The heavy sand used for the casting mold is historically known as green sand. It is a simple, earthly mixture of silica sand, clay, and just enough moisture to hold a firm shape when squeezed in the hand. The mahogany pattern is firmly pressed into the compacted greensand, leaving behind a perfectly formed negative impression. When the glowing, molten iron is carefully poured into this dark void, it fills every crevice, capturing the delicate filigree of the intended design. As the liquid iron inevitably cools, it undergoes a highly predictable shrinkage of 1/8 of an inch per foot. The brilliant engineers accounted for this exact physical contraction in their initial calculations, subtly adjusting the logarithmic spiral accordingly. Let us shift our gaze and focus on the balusters, the slender, vertical iron supports that exist only to hold the handrail. Each individual baluster is cast separately, designed to slot perfectly into a designated groove on the far outer edge of the tread. The top of every baluster angles perfectly to meet the sweeping, continuous curve of the handrail above. The handrail itself was often formed from a slightly more pliable wrought iron, capping and completing the rigid structure beneath. The combined weight of the handrail and the numerous balusters presses down firmly on the outer edge of the treads. Without proper engineering, this could create a dangerous torque, violently twisting the treads away from their central column. However, the methodical Victorian engineers solved this issue with a very discreet, overlapping mechanism. The back edge of each iron tread rests ever so slightly on the front edge of the tread directly below it. This gentle overlap successfully transfers the weight from one step down to the next, continuously cascading the load down the outer perimeter of the spiral. The staircase effectively becomes a continuous, self-supporting ribbon of heavy iron. The intense compressive force bearing down on the central column is perfectly balanced by the interlocking strength of the outer perimeter. It is a profound state of equilibrium, born of mathematics, frozen forever in heavy metal. Imagine the slow, highly methodical installation of such a heavy staircase in the corner of a grand, dusty library. The central column is erected first, plumbed perfectly vertical by a worker, using nothing more than a simple lead weight on a long string. Then the heavy treads are lowered, one by one, sliding slowly down the central column with a soft, resonant, metallic scrape. Step by step, the heavy spiral rises from the floorboards, winding its way upward toward the plastered ceiling. The diligent workers apply a thin, smooth layer of lead putty between the overlapping collars of the treads. This soft putty gently cushions the raw iron, silently absorbing any potential squeaks or groans as the staircase inevitably settles into its final posture. The sheer repetition of the construction process is deeply hypnotic. Lift the heavy iron, align the collar, lower it down, and let it settle. Lift the iron, align the collar, lower it down, and let it settle. Once every single tread is finally in its rightful place, a heavy, decorative iron cap is threaded onto the very top of the central column. This simple cap effectively locks the entire intricate assembly together in a permanent state of tension and compression. The flawless mathematics of the spiral actively ensure that no single point bears an undue or dangerous burden. The physical force is evenly distributed, entirely diluted by geometry, until it becomes nothing more than a gentle, constant pressure on the floor beneath. The cast iron, which was once a bubbling, chaotic liquid in a fiery furnace, is now a perfect symbol of order and unwavering stability. It stands quietly in the dim shadows of the room, a permanent testament to industrial patience and mathematical law. The ornate filigree patterns cast into the surface of the treads serve a brilliant, dual purpose. They please the eye with repetitive geometry, but more importantly, they provide necessary physical traction for the smooth, leather-soled shoes of the era. The structural, empty voids, designed within the pattern, cleverly reduce the overall weight of the massive casting without compromising its vital rigidity. It is a masterful exercise in architectural efficiency, finding literal strength in the quiet absence of material. Let your mind gently trace the slow, rising curve of the smooth handrail. Follow it as it loops patiently upward in a perfect, continuous, and completely unbroken line. The overwhelming complexity of the engineering design slowly fades into the incredibly simple reality of its mundane function. A spiral staircase is, ultimately, merely a functional tool used to transition from one elevation to another. There is absolutely no urgency required for this transition. The steady, predictable spiral dictates a measured, deliberate, and unhurried pace. As we quietly contemplate the silent endurance of these heavy iron structures, the immediate, frantic worries of the day begin to completely lose their sharp edges. They crumble effortlessly away like dry molding sand, leaving only the sturdy, foundational facts of geometry. The perfect structural equilibrium of the iron beautifully mirrors the slow settling of an overactive mind. The internal tension is finally released, safely distributed downward into the solid ground. The logarithmic spiral continues its gentle, endless rotation, remaining a dependable mathematical constant in a rapidly changing world. It is a highly predictable, incredibly dependable shape that asks absolutely nothing of you. Close your eyes and easily visualize the smooth, cool surface of the ancient cast iron. Feel the solid, completely unwavering support of the geometric lattice, holding steady in the dark. The factual history softly blurs into the distant background. The roaring foundry fires have long been extinguished. The brilliant engineers have all gone home to rest, and all that remains is the silent, sturdy spiral. You are peacefully left in the quiet, empty library, completely surrounded by the calm certainty of mathematics. The slow, rhythmic, predictable winding of the staircase leads you gently downward into a deep, untroubled, and heavy rest. Discover more history by watching the next video. We're eager to share more with you. You can't go wrong. All our videos are deeply detailed, dull while fascinating, and distinctly sleep-inducing.